Okay, so thank you all for joining us again today. Hello, Hafaday, and aloha to everyone. This is the first webinar in the Pacific Desk 2021 webinar series. I'm David Hitzel. I'm usually the Guam Pacific Desk Guam instructor. And today we will be discussing the topic of inundation as it affects low-lying Pacific Islands. As a reminder, this webinar is being recorded for educational and documentational purposes and will be broadcasted on Facebook Live simultaneously. If it's not there, it should be there. If it's not, then somebody send me a message. Please refrain from having your video or audio on while the webinar is ongoing, unless you're actively asking a question. If you want to ask a question during the webinar, please do so in the comments section, and I or Jennifer will be checking that. And lastly, the video recording will be saved. So I will be sending out an email with the link to the video fairly soon. And then in the long term, you'll always be able to find the link to the video on our Pacific Desk website. Okay, so just a brief mention about upcoming Pacific Desk webinars for this spring. So I'm already working on one that has to do with wave modeling specifically. So last season in the fall, we did the wave surf forecasting webinar. And it occurred to me that it might be useful to do one that just focused specifically on wave modeling, since out in the Pacific, we're dependent on those to a great deal. So that will cover the spectral models, the global wave models, some basic ocean wave theory, and then the second portion, the second speaker will talk about the nearshore wave models and how those are affected by local winds and local bathymetry. And then later on in the spring, I'm planning on putting together a disaster management webinar. If anybody has suggestions or there's a topic that you would like to see, please get in contact with me either directly or through the Pacific Desk. Okay, so today's speaker on inundation as it affects the low-lying Pacific Islands is Maurice Vondruss. He is a physical oceanographer at the Geoscience, Energy, and Maritime Division of what's called the Pacific Community, SPC, and he's based in Fiji. His research focuses on understanding wave processes on different temporal and spatial scales using a wide range of numerical models and observation platforms. And since he joined SPC in 2017, he has been specializing in coastal hazard and vulnerability assessments and in the development of operational impact-based multi-hazard forecast systems for low-lying island coasts. So this is his area of expertise. I usually put together an introduction for these webinars. It occurred to me that before I did this, that coastal inundation is not actually part of the core course of the Pacific Desk instruction at this time. Who knows, maybe it will be in the level 3. But I had to go and do my homework to make sure that I knew what to say about this topic. But I thought it was important to give some general context and point out the common factors for inundation. So my experience with inundation primarily comes from what would be characterized as nuisance inundation in Honolulu. So we periodically have high surf and coinciding with high or king tides. And this can lead to flooding along beaches where the waves come on the sidewalks or sometimes on the streets and disrupt traffic. We also have if you've lived in Hawaii for a while, you might be familiar with what the local words mean. And Waikiki actually means freshwater spring. So the Waikiki region used to be a swamp. It was a brackish water area. And so much of it is not very, very high above sea level. And this includes other regions of Honolulu too. So this picture on the lower right-hand corner shows a region where this is not due to surf, this is just due to high tides. This area of town is barely above sea level, and the storm drains, they drain to the ocean from this region. So when the tide is particularly high, the ocean comes back and floods the street. So this is actually a fairly common problem, and I think there's some subsidence, there's sinking of the land going on in this region. But most often what's talked about in terms of inundation in Hawaii is future sea level projections. Because much of it is not too much above sea level, there's big impacts that could happen, and there's a lot of modeling work done to predict how this might look. Okay, so in terms of coastal inundation, for low-lying Pacific Islands, there's basically two timelines and several factors that go along with each of these. So the two timelines are what you would call episodic and chronic. The episodic ones are these periodic events that usually involve large waves and high tides. And then the chronic sea level issue, it comes from global warming and sea level rise. So episodic, it almost always involves large waves, and therefore these are seasonal events. They typically occur in the winter season when large swells arrive from the mid-latitude storms. Swell direction is an important component of this. So some coastlines of the low-lying islands are better protected than others, and you can even get inundation from the lagoon side of the island. You don't necessarily have to have a high tide if you have large enough surf, but these two things often coincide, creating the inundation. And then, of course, with tropical cyclones and even strong monsoon winds, you can also have large waves and higher than normal sea level. The chronic inundation, if you have an area that's just geographically predisposed, barely above sea level, then this is, you tend to have repetitive inundations, and the sea level rise component, which can be either global warming related, or it can just have to do with pre-existing cycles like the El Nino cycle. And the impacts of inundation can be from nuisance to severe. So the nuisance flooding would be cases where there's no permanent damage. In severe cases, you can have buildings that are basically destroyed. There can be transportation disruptions, water supply contamination, other sanitation issues, and damage to crops and ecosystems. Okay, so forecasts of inundation events and estimations of their severity are important to local populations, so that action can be taken in advance to protect life and property. The short-term forecasting, this is basically identifying periods when high tides and large surf will coincide. So this is dealing with the episodic inundations, but models can estimate the impacts of a specific set of variables. So it can tell you hypothetically what will happen if you have surf coming from this direction at this size. And then the mitigation in those situations would be evacuations and reinforcing existing structures and seawalls. But for the long term, we use model projections of how sea level rise will affect existing island elevations and their infrastructures, and with consideration of how to adapt those infrastructures. One of the interesting things I was reading about was that Majuro in the Marshall Islands, which often has inundations, they were going to build a new sports a structure for local sports, but they were going to try to make it in a way so that it would act as a seawall at the same time. So one wall would act as a seawall. So these things can, with the model projections, these future infrastructure changes can be best set up. Okay, so with that, I think that covers enough ground on inundation. And with that, I'll pass it to Maurice.
Awesome. I'll share my screen again. Yeah, that was a really nice introduction. You can see my screen, yeah?
Yep.
Cool. Yeah, so as David said, I'll be talking about inundation forecast systems and particularly how we're developing them here at SPC, specifically tailored to regional Met services that often have lower computing facilities compared to, say, NOAA and a lot of the big agencies. This work, it's not only myself, but also my team members. I want to acknowledge Antonio and Hervé especially. Between the three of us, we're doing a lot of the modeling here with other colleagues, obviously. Just if you don't know what SPC is or who SPC is, we're a regional organization. It's an intergovernmental organization with 26 member countries, and we're working across a whole different disciplines, including geoscience, energy, and maritime division, which is where I'm working. We have 26 member countries, so it's most of the Pacific Island countries, and including the big surrounding countries, Australia, New Zealand, and United States, and also France, because of the French affiliated territories in the Pacific. So this is the area I'm working in, and our team is working in. So we obviously have oceanography, ocean and climate monitoring. We're looking at coastal hazards, which is what I'll be talking about today. But we're also looking at water quality. We're doing hydrographic surveying, habitat mapping, marine geophysics, looking at resource management, and deep sea minerals. So those are just the fields that we're working in. And maritime boundaries, which is a pretty big team in our division as well. Our team specifically has kind of these four pillars that we're working on. So this is one, coastal monitoring. So in situ observations for long-term monitoring purposes and to observe changes. We're developing numerical models, doing coastal hazard assessments and developing early warning systems. And we also do a risk assessment. So translating the hazard into risk. Coastal hazards, obviously, if you guys live in the Pacific, you're aware that that's a really big issue. And a lot of times lives and livelihoods are disrupted, like David already introduced really nicely. So there are different processes that are impacting our, basically the wave run-up, or that determine how far the water will come up to shore. So for once, that's the tide level that you can see here in the offshore, and the storm tide level. So if you have a storm, the water level will be higher than with just the tide. And then on top of that, you'll have the different waves. So you can have different storm patterns that are generating different swells that all work on top of each other. And then as you go in the near shore, you get breaking waves, and then you get nonlinear processes on the reef that occur due to wave breaking, like wave setup, for example. And then you have swash motion due to infragravity waves as well. And all that is influenced by the reef morphology and beach slope and so on. So and then obviously also the topography. So it's quite complex, and we're working with a lot of different variables. So how do I make an informed decision if my coastline is going to get inundated, be it in a hazard analysis or be it for a forecast system? So if I want to assess the coastal vulnerability, like I said, we have all these different variables that we're playing with. We have the bathymetry, we have the morphology, topography, the tides, wind, wave conditions, and then long-term sea level variability, like El Nino, La Nina, but also sea level rise and so on. So how do we put that together and come up with some system that then predicts events such as this? I don't know if you can see this, hopefully. So this is a swell inundation event in Nanumanga in Tuvalu during Tropical Cyclone Pam. And what's interesting about this event is that the Tropical Cyclone Pam was about 1,000 kilometers away from that island. And so the waves that were generated in this storm traveled over 1,000 kilometers to then reach the coastline. And yeah, this is kind of what happened. And so you can see it almost looks like a tsunami, and that's this infragravity wave motion that inundates the coastline, even though the actual waves offshore are at a lower, or at a higher frequency, at a lower wave period. You have these long waves that travel up the coastline and cause a lot of destruction. And so if we want to predict these events, we need to take all these physical phenomena into account. Now, yeah, we can look at all those, and obviously all of those interact with each other. And unfortunately, that happens at like a nonlinear scale. So you can't just say if one gets bigger, everything else gets bigger or smaller. So how do we deal with this? This is a kind of a schematic of an operational forecast system like we would develop it. So first of all, we have mean level of the sea that we need to take into account, and we have tides. And those two together, we can have a water level forecast. And that's for offshore. So mean level of the sea we can get from satellites, or we can get that from global models that assimilate satellites into them. And the tides we can get either from local tide gauges or tide observations if they're available, or otherwise we can use a global tide model. Then we have wave and wind conditions. We can use those from global forecasts. And the problem is with those, and I'll show that in a slide later, that those global forecasts are very good on like a basin scale, on an oceanic scale. But if you're actually only interested in one small coastline or one island, a lot of times, especially in the Pacific coast, a lot of the islands tend to be quite small. The global wave models don't actually resolve the wave processes around these islands. So we need to downscale our wave models to resolve the processes around our islands. Once we have our local wave conditions and we have the water levels offshore, we can come up with a run-up forecast that takes into account all those nonlinear processes that occur on the reef as the waves break and so on. Obviously, we always want to validate our models. So we also ideally have real-time wave conditions and water level conditions that are being monitored that can feed directly into our forecast system as well. And once we have all that, we have this run-up forecast that can then be translated into something that citizens can understand. So this is where then usually the Met services take over and translate the pure numbers into a forecast or a warning for the population. So this is kind of the schematic of what we're doing or what we're trying to do. And now I'll explain a little bit how we're actually doing it. So first of all, the most important thing that we need is baseline data collection. I'm not sure if you can see my full screen because I have the images of the like all the faces on my screen, so I'm trying to move it around a bit. So the first thing, or the first problem that we face when we're trying to do a hazard assessment or if we're trying to develop a forecast system is that in most places, we don't actually know where the mean sea level is. Now, in places like Hawaii, that mean sea level would be quite well established. But if we go to some remote islands and remote areas, we have no idea where the mean sea level is in relation to the land. So the first thing we need to do is a geodetic data collection where we actually establish a vertical reference datum on land, and we can tie then the land elevation to the water level. So we have to install a tide gauge, and then you measure the water level over a certain period of time, and then that tide gauge is kind of tied into a global reference system. So once those are all tied together, we can come up with a bathymetry topography data set that actually tells us where we are in relation to the globe. And the next thing is we want to collect oceanographic data, mainly to calibrate our models and to reduce uncertainties and to ensure that what our models tell us actually makes sense, and that's what we're actually observing in reality. So before every one of these developments, there's a lot of groundwork that has to be put in, which with this current travel situation makes our job pretty hard. So this is an example of a tide gauge, and a lot of those, unfortunately, and especially in the capital islets in the region, we have tide gauges. But again, like I said before, if we're going in some remote area, we need to deploy our own temporary tide gauge. So those measure sun, moon, well, like astronomical tides by sun and moon. And on top of that, it also measures the sea level anomalies. And then we can use global models. Like this is an example from HICOM, which is a global model. And we can use mean sea level anomalies from there. And we can use our tide gauge to validate that the model is actually doing a good job in our location. So that then gives us mean sea level offshore and the tide conditions. Now, the waves are a bit more complicated. Like I said before, in most places, we can't just use a global wave forecast or a global wave model. Here on the left side, you can see an example of Fiji, and you can see all these scattered little islands. And basically, the global model that you see on the left just shows one color that represents the wave height. And you can't actually see the effect that the islands would have on the waves. So what we need to do is we need to downscale our wave models. So on the right side here, you have a picture, a bit zoomed in, of the main island of Fiji, Viti and some small islands around it. And you can actually see the wave shadow. So you can quite easily see that the wave heights. So obviously orange and red colors represent larger wave heights. So the swell would be coming from the south. But then the waves would be sheltered in the lee of the islands in quite a few areas here. And those are things that we need to resolve if we want to figure out if a certain area of coastline will get flooded or not. We need to know if the offshore islands actually have an impact or not. So these are some other examples of wave models that we're currently, or that we have developed over the past couple of years. In the left is a model of Tuvalu. It's a country scale, so you can see everywhere where the black becomes like more intense is where the model resolution gets much higher. So we're using an unstructured mesh, which allows us to have a relatively coarse resolution in deeper areas that we don't care as much about, and a really high model resolution around the islands where we want to have really high accuracy. In the middle here, we see our model for the Marshall Islands. And then on the right side, we see a model of Tarawa. We have a larger scale model of some areas of Kiribati with a really high resolution area around Tarawa. And yeah, you can see, so the model resolutions of these models goes down to, in Tuvalu and Marshall Islands case, around between 150 and 300 meters around the islands. And in Tarawa, I believe it's around 15 meters or so. So we can resolve a really high resolution in the areas that we want to resolve. Now that gives us the offshore wave conditions. And here you can see some historical time series. So in the top graph, we have the significant wave height from 1990 to 2019. Below that, we have wave periods. Below that, we have wave direction. And below that, we have the offshore sea level. So that's the sea level anomaly plus the tides. And that's great. So now we have a bunch of historical simulations, essentially, and we validated them, and we know, okay, that's what we simulated is good, and it's good for offshore. But what does it actually mean for nearshore and for the wave run-up and for the inundation? So for that, we use a different model that plugs in the wave height, the wave period, the wave direction, and the water levels offshore. And we plug it into our model that resolves the actual wave motion and wave breaking across the reef, and then the wave run-up. So in this case here, we use a well-established model, XBeach, in non-hydrostatic mode. And this example here is for Funafuti in Tuvalu, so the capital atoll of Tuvalu. And in the top graph, you can see the waves coming in. So red, higher water levels, blue, lower water levels. So you can actually see the kind of up and down motion that you would expect from a wave. And then in the bottom left, you have the current velocities, and in the bottom right, you have the actual inundation. So as the water overtops the berm, you get water penetrating the island, and you actually have the island gets inundated. Now that's great, but there's a big problem with this, and it doesn't really work as an operational forecast system. And the problem for that is that it's incredibly slow to compute. While it looks really nice and smooth in the animation, to actually compute, say 2 or 3 hours of run up actually takes us up to a day of computational time. And so if you want it as a forecast system, you don't have enough time to actually run the model to then give out the forecast, because by the time you're done running the model, the event has already occurred. So we need to come up with a way to shortcut this whole thing. And we do that by applying some statistics and some machine learning. So the first thing we do is we look at extreme values over our historic data set. So we look at our past 20 years, and we look at the extreme wave height, wave periods, and so on. And we put them into relation to each other, and we're getting the distributions using a kernel distribution. I'm not going to go into too much detail because that would be quite complicated and probably take too much time. But in essence, we look at the relationships between wave heights, wave periods, wave directions, and also the mean sea level anomalies, because all of those kind of interact in some way. But for a start, we don't really know what way they interact. So for example, as an assumption, we can assume if we have larger wave heights, we potentially also have longer wave periods. And that's not always the case, but yeah, anyway, we're looking at all these interactions between, and then we can do something that's called Monte Carlo simulation, which is essentially creating a bunch of synthetic events, synthetic extreme events that are all based on our historical data. So those events did not happen over the past 10,000 years, but based on statistical probabilities, they could have happened. And some events are more likely than others. So that's a quite normal or a quite standard way of creating more data in an area where you don't have enough data, which in case of extremes, we don't have enough extremes. So once we have our 10,000 years of extremes, so these are not time series, but these are just in the top wave height, the bottom wave period, the second row is the wave period. And then we have the mean sea level anomalies and the tides in the last one. We have a bunch of data, and So now we need to come up with a smart way of actually translating that into inundation, because again, those are offshore conditions. So the first thing we can do with the data that we already have, which is quite useful when we're looking at hazards, we can look at return periods, because now we have 10,000 years of synthetic events. We can actually just plot them on a logarithmic scale, and we can come back with return periods, and we can look at, okay, how likely is it that we have a wave height that's 3 meters? So that's really useful for coastal engineering, for example. And even though we don't have a record of 100 years, we can actually tell what our one in 100 year event is with this methodology. Now, we still want to be able to forecast extreme events. So the next thing we do in this methodology is we actually pick different events from these 10,000 years of synthetic events. And the way we do it is by using this maximum dissimilarity algorithm. Now, the way I like to explain that is, and it works quite well, at least in Fiji and countries that play rugby, I like to explain this algorithm with rugby players. So assume you want to have a statistical representation of rugby players in Fiji. Now, one aspect you might be interested in is how fast are rugby players. So you look at the speed of all the rugby players in the league. And one way of looking at this is, okay, who are the 5 fastest players in the Fijian rugby league? Now, but we want to actually explore the entire space of our variables. So what we do is we're not only looking at the fastest rugby player, but also the slowest rugby player. And then we're looking at some rugby player who's like in the middle. Now, the next thing we might be thinking if we're exploring Fiji rugby is, okay, how strong are our Fijian rugby players? So then again, we're looking at the strongest Fijian rugby player and the weakest rugby player. And then we put the strongest rugby player in relation to the fastest rugby player, in relation to the weakest rugby player, in relation to the slowest rugby player. And we do that across a bunch of different dimensions. And obviously we're not looking at rugby players, but we're looking at water level conditions. So we're looking at significant wave height, we're looking at wave periods, wave directions, and the total water level offshore, so tides and mean sea level anomaly. So in essence, we're putting the largest wave heights in relation to the smallest periods in relation to the highest periods, and so on, if that makes sense. Now we'll select 500 cases. Now those 500 cases, we actually go and simulate with our computationally expensive model. So 500 times we have to run this model with all these green dots that you can see in the left graph here. So all these green dots represent scenarios of, well, combinations of water levels and wave conditions. And all these 500 cases we simulate. And then we feed all these into a radial basis function, which is essentially an artificial intelligence or a machine learning algorithm that works really well across multi-dimensional space. And since we have so many different variables, this works really well. So we use those 500 cases to train our machine learning algorithm. Now, this is an example why this machine learning algorithm is so powerful. So we did a comparison, and we simulated this time series on the right-hand side using a dynamic X-speed simulation. So really running, I think it was 16 hours of water levels, like run up in a certain location. And we used our machine learning algorithm, our radial basis function, to do the same computation. And on the right-hand side, you can see the red graph is our machine learning algorithm, and the black graph are our dynamic simulations. In order to simulate those 15 or 16 hours dynamically, so with our non-hydrostatic wave model, it took us over 5 days of computational time. With our radial basis function, it actually took less than 1 minute. So you can see why this is really powerful as a forecasting tool, because you can display incredibly complex scenarios and really fast. So two ways of applying this. So the first one is you can then actually go, once you have this, you trained your machine learning algorithm using those 500 cases, you can actually go and reconstruct all your 10,000 years, because it's much faster. You don't actually have to run it all. And then you can come back with return periods and estimates of how likely it is that a certain area of a coastline will get flooded or not. So here on the left side, and this is just a schematic, we have a certain return period of assumed water level near the shore. We look at the wave height, wave period, wave directions, and sea level anomalies and tides. During that return period, we feed that into our radial basis function, and then it spits out an inundation map. So we can immediately say, okay, like with the present climate, we have a 1 in 100 year chance that a certain will get flooded or not. And then obviously then the next thing where this becomes really powerful is if we're actually looking at a forecast. And so this is an example of a forecast system that we have developed. So we use our downscaled wave model in the top left here. And we use our water level conditions from a global database like HICOM or satellite observations. And we use our tidal predictions. We feed them into our radial basis function. And right away, we can have a forecast. So for the next 7 days, or for however long we're running our forecast. And not just do we get a wave forecast, but we also immediately get a total water level near the shore that's indicated here by the gray shaded area in the bottom plot. And as soon as we reach a certain threshold, we can tell the machine learning algorithm, okay, once we think we're in a really high water level near the shore, give us an inundation map, because we think this area is going to get inundated. Now, we have, like I said, we have a few of these systems that are currently under development. One has already been trialed and has been trialed for a couple of years here in Fiji now. And so this is one event that we had in May 2018. We had extremely large water levels. So this is from our regional downscaled wave model. So you can see we have wave heights exceeding 4 meters from the southwest. And then on the right side, you can see a time series graph of wave height, wave period, and wind speeds. And you can see that the wind speeds aren't incredibly high. So this is really from a swell that was generated off New Zealand and propagated all the way up here. And yeah, obviously we have really large waves. So our inundation forecast then gave us total water level near the shore, and it showed us, okay, a lot of the day, or like there's a high likelihood that we're going to get into the red dangerous area. And it also spits out an inundation map. So this is a part of Fiji's south coast, along Fiji's main island. And you can see that little island here, for example, that's a hotel. And yeah, obviously if there's inundation, then that will lead to a lot of disruption. And you can see also that there's a predicted inundation along the village, kind of in the middle of the figure. Now, Fiji Met Service then gave out a warning, and they said there's a very high chance that waves will overwash into the vegetation line and to low-lying coastal areas. And so this was like our first big success, because the theoretical model that we came up with and the system that we came up with for the first time was actually used by the Fiji Met Service. And sure enough, it led to inundation, and properties got flooded, and yeah, there was some damage. Now you can think, okay, well, it was a 4-meter wave event. That's quite likely that there's going to be some flooding. So only 2 months later, we had another event. But this time, the offshore wave height was only predicted to be about 2.5 meters. But because of the high tides and high mean sea level anomalies, and because of the swell direction and the period of the swell, our forecast system again told us that there might be some inundation. And again, Fiji Met Service gave out a warning, and again, there was some inundation. So that was, well, within 2 or 3 months, the second positive feedback, or yeah, positive trial of our forecast. And since then, there have been a few more instances where our forecast predicted coastal flooding. Now, this already kind of brings me towards the end. Inundation events, as we covered, are compound events. So it's not just wave heights that are important, but it's wave heights, wave periods, wave directions, mean sea level anomalies, tides, and to actually resolve all those is quite complex and quite complicated. Wind-generated waves are one of the main drivers for coastal inundation in the Pacific. And those can be, like we saw in that video in the beginning, they can be by cyclones that aren't even in close proximity, and we can still have inundation because the waves that are generated by that cyclone still travel and propagate across the basin and flood the area. Metamodeling, which is this technique that we've been using, provides a very practical and computationally inexpensive way to assess the inundation. So rather than to dynamically simulate everything, this metamodeling technique makes it computationally feasible to actually have the system deployed in a regional Met Service without the use of supercomputers. So the forecast systems for Fiji, Tuvalu, and Kiribati are currently under development and are being deployed in those countries. In Fiji, it's already deployed, and Tuvalu and Kiribati, they will be deployed this year. And we are at the same time using the same but similar methodology. We're doing a coastal hazard analysis in Majuro and the Marshall Islands, and we're looking at ways to turn this into a forecast system. And we're currently talking with PEC-IUs and NOAA to basically integrate that, like our methodology, into their already existing coastal inundation forecast system. So we can actually compare the different methodologies, and so that's really exciting work that we're looking forward to collaborate with PEC-IUs on this project. And that's it. Thank you very much.
Maurice?
Yes.
Maybe you have to stop sharing your screen.
There you go.
All right. Thank you, Maurice. That was great. I really like webinars where I get to learn stuff that I've not heard about before. So that was very interesting. So we have time for questions. I had at least one in the chat here. Tom Evans asked, how can the model run so fast? Is the machine learning algorithm based on data mining of the dynamical model?
Yes, that's exactly what it is. So essentially, this machine learning algorithm is a very fancy interpolation method, and because we're creating these artificial 10,000 years of events, we create very, very extreme events. So that even cover events that are very, very unlikely, like 1 in 10,000 years or so. And then with this interpolation method, we don't actually ever have to extrapolate, which is kind of the benefit of using this radial basis function. So yes, essentially, so we generate those 500 events, like I was saying, and those 500 events are very extreme events and very unlikely events. And then using this machine learning algorithm, because our realistic scenarios are likely going to be somewhere in the middle of these extreme events, we then use this radial basis function as an interpolation method, if that makes sense.
Tom says, thank you for your insightful presentation. Also, Alex Relifia asks, are there any forecast systems planned for the Solomon Islands?
Currently not, because so one of the problems that we have at the moment is that we're very reliant on project funding. But if Solomon Islands are interested in having a forecast system, then it'd be great if you could contact me or us, and then we can look at ways of how we can potentially bring this forward. We know early warning systems have been raised by the Pacific Met Council as a high priority area. So if the Solomon Islands would like to have a system like that, then yeah, please do contact me, and I can't promise that we can start working on it this week, but then we can work on ways forward how we can make this happen.
Okay. Alex said again, very nice presentation. So Teddy Allen, who I just learned is from Barbados, he says, Maurice mentioned earlier that big waves are associated with long periods, but his conclusion states that the wind waves are one of the main drivers for coastal inundation. So should we conclude that big waves are not one of the main drivers of coastal inundation? Also, I noticed 30-second periods in his model simulation time series. Does this contribute to a source of uncertainty given the fact that 30 seconds is very large?
Yeah, very good question. So that was just an example that intuitively we would think large waves and long periods go hand in hand, but that's not always necessarily the case. And by wind waves, I include swell waves as well. So I include everything between 1 second and 30-second period. So yeah, if that answers the question. So I wouldn't say that big waves are definitely one of the main drivers of coastal inundation, but big waves with long periods are potentially more dangerous or more destructive than big waves with shorter periods, for example. Now, with a 30-second period, that's a great question, and that's kind of what I was hinting at in the answer before. So we're really trying to cover the most extreme cases. So in reality, we might never get, and again, this is just at the top of my head, but we potentially might never see a 10-meter wave at a 30-second period in a certain location. But we want to simulate this event anyways. So our machine learning algorithm later on can interpolate from this really extreme case to a more realistic case. So yes, it probably wouldn't contribute to a source of uncertainty. But then it's also, I mean, obviously it's a question of how well our model could actually simulate a 10-meter, 30-second wave, because we wouldn't have any in situ observations to actually validate the model. But yeah, at some point we have to assume that our model holds valid over these extreme cases.
Okay. We have a question from Patrick Chan. Hi, the forecast office on Guam is trying to improve our accuracy on inundation forecasts on Majuro. Can I correspond with you after this meeting?
Yes, of course. not sure what I'm assuming it would be a similar system that is being used by or that has been developed by HackIUS and NOAA. And like I said, we're working closely together with them. So I'm happy to catch up and see of ways how we can all work together. I think it's great.
Yeah, I kind of wanted to mention that the only reason that I'm conscious of this idea of coastal inundation and frequent coastal inundations comes from being in Guam and hearing about the inundations that happen in the Marshall Islands. So if there's anybody here from the Marshall Islands that wants to, add an anecdote, something, their experience, something that could be better addressed by these models, feel free to comment on that and let me know, and I'll give you screen time. Another question from Silipa. Ideally, how many buoys per 10,000 square kilometers of ocean is required for a reliable wave model?
So yeah, I don't think there's a one-size-fits-all answer. The more buoys or the more in situ observations we have, the better. And unfortunately, the number of observations, especially in the South Pacific, Southern Hemisphere, is very low. I know a lot of US affiliated countries are lucky to have wave buoys, like Marshall Islands, for example, have a wave buoy. And I believe Guam might as well, but don't quote me on that. We're slowly starting to change that in the Southern Hemisphere. So we currently have a project where we deployed a few wave buoys along Fiji's south coast. And we're also deploying wave buoys in Tuvalu and Kiribati as part of this inundation forecast system. Now, another thing that we have tried to do, and unfortunately so far it hasn't really been successful, we deployed a buoy in New Caledonia to act as a sort of early warning system for swells coming from the south, because New Caledonia would get their swells about 12 to 24 hours before Fiji gets them, and another 12 to 24 hours before Tuvalu would get the swells. So in that sense, if New Caledonia sees that the buoy is picking up, then we can assume that the swell is on its way and will hit Fiji shortly. So yeah, there's no answer of how many buoys per square kilometers, but ideally you have a couple of buoys per model. If you don't have that, then you can always rely or use satellite altimetry observations that are potentially not as accurate as buoy observations, but in turn they give you a much larger spatial coverage, so you can use those as well, and we do that as well to validate our models. So the short answer is as many as possible, but obviously that's tricky.
Okay, a couple more questions. Is that all right? Do you have time?
Yeah, of course.
Okay, great. So Mark asks, ideally, how many GCPs per 2 kilometers squared of topography is required for a reliable topographic baseline?
I am not a geodetic surveyor, so I don't want to say anything wrong. So I would, Mark, I mean, I've met Mark, he can probably answer that question better than I can. But yeah, if I can refer you to my colleagues who work in geodesy, but I can't actually give you an answer to that.
Okay. I can't either. I can't provide that answer. Aloha, this is from Max. How is this data info being integrated into the National Adaptation Plan / planning in the RMI? Yeah, so this project
the coastal hazard assessment that we're doing in Marshall Islands is really to inform kind of the status quo of coastal hazard, and will then most certainly feed into adaptation measures and development of coastal infrastructure. So that's kind of the plan. And that's also, so for Marshall Islands, we were lucky in our project to be able to procure LiDAR data. So we actually had a plane, not us, but we got a company to fly and collect really accurate high resolution baseline data for all of Majuro. And yeah, we're hoping that on top of the hazard information that we're producing will form a really solid baseline for the National Adaptation Plan.
Okay, Chip in Guam has asked, have you looked at any events where the islets were flooded from the inside of the lagoon, where the lagoon is flooded from all directions during high tide?
That's a great question, and that's something we're working on at the moment. So if you're, I don't know if you remember, but the model that we have in Tarawa, in Kiribati, in that model, we actually resolving the lagoon as well as the offshore. And in a lot of areas, we actually, there's reports of inundation coming from the lagoon side. So a lot of times you think, okay, if the waves are coming from the ocean side, and so you go further inland, which on an atoll is not very far often, but there's a lot of hazard that can come from the lagoon as well. And we're working on a methodology to predict coastal inundation from the lagoon side as well. So from inside an atoll, be it through wave setup, wind setup on top of waves. That methodology is a little bit different because we don't have some of the processes that we have offshore, like we don't have these steep reefs that lead to very abrupt breaking. But on the other hand, we have wind setup because the lagoon essentially is like a lot of times it's like a closed basin. So if we have wind coming from one direction, that alone can lead to coastal flooding. And I know, for example, in the Marshall Islands, people surf inside the lagoon because the swells penetrate the channel, and then yeah, there's waves inside the lagoon. So that's something we're still working on, but it's not finished yet, so I can't show you anything yet.
Yeah, that reminds me of one of the anecdotes I heard while I was in Guam. Was this must have been El Nino time, 2015, 2016, where there was flooding on the inside of Majuro due to the monsoonal winds. So this is the well-populated area, not very high elevation, but because of the fact the high tide and the wind blowing from that particular direction actually created an inundation event. Okay, and actually Lee Jacklick from Majuro commented that their inundation events in the Marshall Islands are noted to associate with long period waves coinciding with high tides and particularly northeasterly swells. Lee, do you have any what do you guys do in terms of preparation for these events, or how do you adapt to them? Are you still there? Do you have any comments on?
Yeah, David, can you hear me? Yes, David. We are using a combination of warning forecast from the Weather Service Forecast Office in Guam, along with PAC-IU's wave runoff forecast. Mm-hmm. And inundation in the Marshall Islands, particularly in Majuro, it could be attributed to the fact that these islands were were a series of isles that were connected together. So whenever there are large event where there's a large event of long period waves or swells that tend to eat the northern exposure of the island, which is often, then there is bound to be a buildup of water within the lagoon area, and there is not enough outlets for the pressure to be released from within the lagoon. Then that's where we got inundation. But then inundation from the lagoon itself is very calm. There is no wave axis. It's not even driven by wind waves. So it just piles off of waters and then eventually comes on land. Where we get inundation from the ocean side, and there's high wave access, particularly associated with high waves or swells. Yeah.
Okay. Thank you.
Hmm.
Yeah. Because I unfortunately haven't been out to the Marshall Islands yet, some of these things are new information to me. Okay, and Max says the National Disaster Management Office very much improved the communication effort alongside the National Communications Agency to send text alerts to community members. Similar observations for Samoa in the spring tide under a cross equatorial northerly winds, a case in February 2020. Major inundation occurred in Kiribati, Tokelau around the same time. Okay, does anyone have any further questions, or maybe I'll let Maurice off the hook. Maurice, do you have anything else you wanna add before we go?
No, thanks for having me.
Yeah, thank you. Okay, so I'm gonna terminate the webinar at that point. Okay, so thank you all for joining us. I'll send out an email in the next couple of weeks about a wave modeling webinar, so please join us again for that. All right.
All right, David.
Yep. Thank you, Sanchez.
Yeah, I was supposed to ask about the moon, the distance of the moon to Earth. Is there any, mechanism or something that could make any possible inundation to the islands?
Yep.
Like an example of
having to do with the tides.
Right.
So, absolutely. Okay, thank you.
All right, bye-bye.